Community, welcome back to the PX4 Developer Summit, Day 2. I have Chris Anderson on the line. He's going to be speaking about PX4 and FAA type certification. Chris Anderson is the CEO of 3D Robotics and a member of the FAA's Drone Advisory Committee, lead the ASTM, behind the ASTM drone type certification workgroup. 3DR is one of the first companies to go all the way through with the FAA new durability and reliability type certification process for low-risk drones, and works closely with Microsoft AirSim team, laying the groundwork for simulated PX4 data to be accepted in lieu of real-world data for some of the required DNR demonstrations. Chris is one of the founding members for Drone Code, overall pillar of the community, and I'm really excited to have him at the Dev Summit. Please, community, let's welcome Chris Anderson.
Thanks, Ramon. I assume we are actually live. Is it showing up on the stream? Okay, very, very good. Hi, everybody. This has been really impressive. I'm so proud to see this community growing. As Ramon said, I've been here from the beginning. Really the beginning, like 2007 beginning. These days, most of what I do is on the regulatory side. One of the curses of being successful in building up a bottoms-up, organization, and then bottoms-up community, and helping, create what we have here today, is that at a certain point you go from the, hey, we're just kind of, working in the gray zone, we're kind of under the radar, we're just, researchers and DIYers, and at a certain point you win, and you're just like, okay, this is real, we're really out there, we're doing, important work, and then you have to comply with the regulatory process. And in this case, the regulatory process was really not designed for what we do. And so we had to help create the regulatory process. And so what I'm going to be talking to you today is about where we stand on that, and an exciting new development. So let me just switch now to my presentation. I hope you can see that. I'm going to be talking to you sort of with two of my hats on, the FAA drone advisory hat, and the ASTM hat, which is the standards body, which we'll talk about in a second. A lot of the things we're talking about have been echoed in some of the previous talks that have been going on, so I'll cite those where relevant. But basically, the big news here is that the big news here is this notion of type certification. And you may ask, why do I need type certification? What's this all about? We're flying fine right now, but the reality is that we are not flying fine. As the IRIS presentation pointed out yesterday, we're supposed to be flying autonomously beyond visual line of sight, doing all those things that drones can do, and yet, today almost all operations are limited to beyond, to within visual line of sight. Under 400 feet, one pilot, one vehicle. Basically, the drone industry has not yet begun. The drones are supposed to be autonomous vehicles flying, anywhere, anytime, under their own steam. And we're still at a one person, one drone world. And the reason being is regulation. Technically, as you've seen over the last 2 days, technically these drones can fly autonomously anywhere. But we're not allowed to in the United States. And by the way, this presentation is going to be focused on the United States and FAA. I'll touch a little bit on parallels elsewhere. So what's stopping it? And if you look at this slide that Iris showed yesterday, the stats, yes, the beyond visual line of sight, waivers have been issued, and yes, there's more of them, but there should be thousands, there should be hundreds of thousands, there should be millions. You shouldn't need waivers at all. It should just be a normal thing. And so we're really waiting for something, and that something is a foundation of safety, which is called type certification, or airworthiness of the vehicles. Right now, the FAA, all the things you've been hearing about, whether it's drone delivery or the IPPs or any particular operations beyond Part 107, have all required a special waiver or an exemption, and the FAA is just overwhelmed by these. Now, that's because they're all different. It's kind of an ad hoc, one-off sort of regulatory process. And what they need drones to start to look like the things they're used to certifying or used to regulating, and that means type certification. But type certification is the kind of thing you heard about with the 737 MAX. It's extremely expensive. It takes a long time. It's designed for vehicles that can be, jetliners. And the question is there a form of type certification that was appropriate for this new class of small unmanned vehicles? And the answer is yes. And not only is the answer yes, but I'll be talking to you about that. And the deadline is actually this year. So many of these exemptions and waivers, and especially the IPPs, which are these pilot projects, are expiring in October, just a few months. And so we need a new form of certification to be able to allow these kind of operations to not only continue, but expand under a process that doesn't overwhelm the FAA. And so the answer is a new form of type certification. I want to call out two more quotes from the IRIS presentation, which I thought really made a good point, which is that although it is a pain to have to go through the certification process, and we've been lucky to date that in the early days of the drone industry, because of things like Part 107, because of exemptions like developer exemptions or recreational use exemptions, we've been sort of spared all this. And it does seem like it's like I thought this is what we're trying to avoid, but in fact, it's actually a good thing to get certified, because it's going to allow us to accelerate from here. It's a little bit of pain right now for a lot of gain later, and this is going to allow this autonomous era of the drone industry that we've wanted all along. The new form of certification is called durability and reliability, and it's basically streamlined. It is supposed to be, compared to traditional type certification, which I'll get into in a second, this is supposed to be fast and cheap, and it allows you to continue innovating, and more importantly, it reflects this new class of FAA regulation called performance-based. So in the traditional form of certification, they actually certify the individual components. So engines have to have, maintenance standards and mean time between failures, and just gets down into every little element, including the software. And so, one of the reasons that the 737 MAX was such a crisis is that the software really had not been, the software is dating back, 30 years, and that it's because it was so expensive to recertify the software. Anytime they wanted to make a change, it was a patch on top of the old software. And so at a certain point, after 30 years of this stuff, the patches outweigh the core code, and it becomes a maintenance nightmare. And that's really where they were. And so the notion is, what if we treat the vehicle as kind of a black box? And you say, look, we don't really need to know, we, the FAA, don't really need to know what's inside it. We don't need to know what the individual, reliability of the components are. If the entire system proves that it does what you say it's going to do, and it's durable and reliable, then that's good enough. And then you can do minor changes, within the vehicle itself, including software updates, as long as it doesn't change these overall performance parameters. And that's exactly what we want. I think that reflects what's appropriate for this class of low-risk vehicles and this pace of innovation. We don't want to have to lock down PX4 on a vehicle and not be able to update it for the life of that vehicle without having to go through certification again. And so, the ability to do these kind of minor incremental maintenance and improvement changes is really going to help us innovate. So who can apply for type certification? This is again a U.S. effort, so you have to be a U.S. company. You have to have what's called design authority. So whether you design and make it yourself, or just design it and have someone else make it, or even work with somebody else who's like an ODM who has components that you can use, somebody needs to be responsible for the design. And that's called having design authority. And by the way, a part of this I know is because 3DRs is going through this process as well. And we're one of the first in, we'll probably be one of the first out this year. So we've been through the entire process. And so we really know it well. And so in the questions, I can talk a little bit about what design authority entails. You have to have a U.S. production facility. And the reason is because they're going to do a production inspection. You need a production certificate on your facility, and that needs to be here as well. And the vehicles need to be in this sort of low risk category, which you probably think of as 55 pounds, but is now expressed in newtons and energy based on the kinetic energy of the vehicle. So it's a combination of weight and speed. TC by itself will not let you do all those wonderful things, but it does make it much easier to get to those other places. So once you have the TC, your aircraft is considered airworthy, and that's great. Then once it's an airworthy, then you have to work with an operator, or if you're like a Google Wing or an Amazon Prime, and you are yourself an operator, you just go to the FAA and say, well, this is how we're going to operate. This is called our ConOps, our concept of operations. Here's the safety protocols we're going to do. Here's where we're going to fly, and what times, and things like that. Now, it doesn't have to be specifically one geography, and that's the difference between this new form and the old exemptions and waivers. But it has to be a certain class of airspace, a certain class of geography. So if you say, we're going to fly over unpopulated areas, that's great. If you say, well, we're going to fly over populated areas of a certain population density, well, then there's a way to address that as well. But once you get that permission to fly under those ConOps, you can basically take it anywhere and any time where those environmental parameters hold. And then once you have that, you have permission to fly under that type certification. There's certain requirements about tracking your flights. If there's a crash, that needs to be reported. And if you want to extend your operations, you just go back and you say, we'd like to extend our ConOps to maybe a higher population density, and maybe some additional tests you do for that. The way this contrasts to the traditional type of certification that Boeing or Lockheed Martin would do is that as opposed to like a decade or longer, it's supposed to take 3 to 6 months. Now, this first one has been we've been working on it for a couple of years now, but this is, once we get this dialed in, it's going to be 3 to 6 months, as opposed to millions of dollars to go through the testing process. This could cost less than $100,000, depending on how much of the testing you've already done. It's only for the small and the low risk unmanned vehicles. So you're not going to be able to make an air taxi this way, but it's a great way for the FAA to start getting some experience with this new performance-based type certification, building up data so that they can extend it to higher risk categories going forward on a data-driven perspective. To get this, you've got to do the demonstrations. They're not tests in the sense, because you've already done your testing as part of R&D. This is demonstrating to the FAA that your vehicle is durable and reliable. There's two classes of these demonstrations. The first one is just a lot of hours. You basically take a representative operation. So maybe you take off, it flies autonomously, for some lawnmower pattern, lands. If that's representative, that's fine. And you just do tons of them. You can see at least 400 hours, and it can go up to thousands depending on your ConOps. And then that you do those lots of times. And then there's a bunch of other demonstrations that you do just a few times, sometimes only once. And this basically demonstrates things like your failure modes, environmental range, et cetera. Now, there's 32 kinds of those, and we're going to be publishing the FAA will publish those as part of its so-called means of compliance, and we're going to be publishing as well in October as part of our ASTM regs. But when you take these 32 different kinds of specific demonstrations about different kinds of flights, different kinds of failures, and then you combine them with all the variations of environment and center of gravity and temperature and air pressure, et cetera, it gets kind of overwhelming. And so we're going to get into a little bit of how to make that less overwhelming possibly with simulation. The FAA nominated me to lead the ASTM counterpart to this, and this is the way it always works at the FAA. So the U.S. regulators, and this is true for regulators around the world, they typically try to use industry standards whenever possible. So in this case, the FAA says this is what we want to see in terms of the means of compliance, but they don't tell you how to achieve it. And then they turn to ASTM and they ask ASTM, the standards body, to put together a working group, and the working group then comes up with a very long, basically, a tutorial on how to deliver the data that the FAA needs. And that's the working group that I lead. We are in balloting right now, so we've essentially finished most of our work. This is just one example of what it looks like. You can see that I've just taken one of the 32, and this is about geofencing. And the first column on the left is what the FAA says they want. They say if geofencing is used to maintain safe operations, demonstrate that the logic works, and that contains the vehicle. Now, then the second column says, okay, here's how you actually do that. Here's the demonstration you do. And then the over on the right, this is an extension of that first column, and it introduces some of the things you should think about. And so, like, this is a particular case where you have two things going on. On one hand, you've got a failure, so it should, under this particular failure, the vehicle should be flying back home. On the other hand, you've got geofences. And one should not preempt the other. So, for example, if you were to fly straight back home, you would actually be breaching a geofence, and there might be, a school there or a building or something like that. So, in this case, you need to demonstrate that your return to home also respects the geofence. And so, this is this combinatorial logic that you need to demonstrate, so the FAA knows it's going to work. Now, as I mentioned, there is a overwhelming, if you look at all the permutations of the tests you need to do and the environmental conditions, et cetera. And let me go back here, just one slide. If you look here, just look at the slide on the right. When you look at all that variations, just look at this is one test, which says, just fly a distribution of, just fly a mission. But then it says, okay, well, you also need to do it with your center of gravity, full forward, full left, full right. You have to move your center of gravity around. So that means your payload, et cetera. And then you also have to do it under, for your high and your low temperature, high and low pressure, humidity, whatever else you specified. And if you look at all the edges and all the corners of this test matrix, you can get tens of thousands of tests, which you normally would have to do. Now, obviously, that's not reasonable. And sometimes you can say, well, look, on this particular vehicle, maybe center of gravity is super important. Fixed doing this particular vehicle, it's not as important. So you just negotiate this with the FAA. But another way to do it is to bring in simulation. This is a big part of what I'm doing right now, and this follows on very neatly from Paul and Guada's AirSim presentation. So we're working very closely with the industry as a whole, but especially Microsoft, on coming up with a way to construct simulation processes that can be acceptable to the FAA for certification. So this diagram sort of shows you how it would work. So the tests are kind of right down the center of your operations, the kind of things you actually encounter all the time. You should definitely do that in the real world, and you should probably do it enough times that you can prove you're durable and reliable. So that's where the 400 hours come from. Then you start to move to some things you encounter more rarely. These would be maybe temperature or pressure, situations, altitude situations, battery situations, power situations that are kind of very unusual. And if it's really risky, and you probably are going to encounter it at some point in your operations, then you should probably do a couple tests to show that works. But then there's a bunch of others where you're probably never going to encounter it, or it's very rare, or you don't think that it's high risk, or it's just that you just want to touch all the edges of the test environment, but you've already done the same sort of environmental testing and a bunch of other tests, and it feels a little redundant. And there's a case for just doing that in simulation, in automated simulation. Essentially filling out your sparse matrix and turning into a dense matrix where you really can hit all the test points, some of them simulated, some of them real. And our objective here with our simulation project is to figure out, how to choose which tests to do in simulation, how to run those simulations so that they're persuasive, and then how to statistically demonstrate that this is high fidelity, there's predictable or has predictive power to the FAA. So this is really exciting. Now there are other non-real world flight options that will also be considered. There's going to be wind tunnel. That's one way to do it. There's benchtop testing. There's environmental chamber testing. All of those can be and historically have been introduced as a kind of an alternative means of compliance. However, I think that given the volume of testing we're doing and given how well this community has aligned around simulation, computer simulation seems to be the one that's new, and we should emphasize the most. So this gives you the obvious pros and cons. The cons are that the FAA really has very little precedent of accepting simulation in lieu of real-world testing. In addition, the FAA is pretty comfortable with deterministic simulation. They don't necessarily love simulation instead of real-world testing, but they get it if it's like if you're doing a binary, like the logic worked or it didn't work. But once you get into probabilistic simulations, it's we need to help us with a statistical model they can understand. And so what we've done is we've basically divided the world of simulation into two groups. There's the system logic And that's kind of binary. It works or it doesn't work. And you saw that, I'm going to cite a little later in the talk, Julian No's presentation, which is excellent. And so what he showed you with the hardware in the loop and software in the loop was largely system logic. And he gave you a perfect example of some kind of combination of GPS loss and battery life and things like that. You just want to make sure that the failure cascades, just kind of all percolate through the matrix of combinations of actions correctly as expected. So that's pretty easy to do in software in the loop and hardware in the loop. And again, it produces kind of pass-fail results. The other ones are all probabilistic, and this is like, this has to do with simulating environments, simulating sensors, simulating wind and things like that. And there you're going to get, it will never be perfect, just because we can't simulate the real world with infinite fidelity. And so it's going to be some approximation of the real world. And the question is it good enough? So this is the way we're going to propose it. That you're going to end up with this. Here's the matrix of all the various combinations. This goes back to kind of Julian's work on the system logic. Here's all the combinations that you might see. I just kind of put numbers up there, but you can imagine what they are. And some of them it was easy to test in the real world. We do have what we call fail boxes that we put on top of a drone. It's really just a box with a separate radio connection, and that box will like cut out the GPS, or it'll cut out a motor, and it'll or it'll disable the RC. And those ones we can test in the real world. And there's a bunch of others that we can't test in the real world, or it's not practical to test in the real world, and those we'll do in hardware in the loop or software in the loop. This is a slide from Julian's presentation. This is one of the pre-recorded ones, and I really would encourage you to go back and look at it. It was fantastic. But just two screenshots from this. On the top right, you can see his hardware in the loop box, and that's great. You can see it's got some motors, it's got some servos, and in that way we can sort of test some basic logic stuff, and then you can automate those tests, especially in both in hardware in the loop and software in the loop. And he talked a lot about how you would do that. So that's a way to really do the logic testing at scale and to help populate the matrix. So I'll leave that to his talk and encourage you to do that. But there's a lot more simulations that need to be done. So those are just the deterministic ones. On the probabilistic ones, there's 6 more simulations that need to be done to essentially fully simulate a vehicle. There's the stuff that's kind of basic aircraft operations. This is what's going to be required by the DNR. There's the physics and dynamics, and then the environment. You have to simulate. You can't just simulate the vehicle. You actually have to simulate the air and the wind and the temperature. So you have 2 simulations there: aircraft physics and then environmental physics. The GE presentation yesterday was also really good on this, and I encourage you to go, if you haven't seen that, go back and see that. They really focus on the sort of the best practice in physics and dynamics, how they found the right ones for them, the pros and cons of the various options. And so I hope to work further with them on that. I was really impressed by that. Then we need to simulate the environment. And the problem with many of the simulators we use today, like Unity or Unreal, et cetera, is that they're really good at simulating kind of video game environments. But what we need to simulate something that's appropriate to FAA, and a lot of this has to do with gusts and turbulence around structures, like in buildings in an urban environment. And this is a very unusual sort of it's fluid dynamics simulation. I'll talk to you a little bit later about the test environment. We're doing some of that right now, but those are kind of that's where we're going to be focusing. And just to give you one example of how difficult it is sometimes to assess the fidelity of a simulator, let's just say that we simulate wind gusts pretty well, we think. Well, how do we compare that to the real world? Well, how do we measure wind gusts across an entire area? In other words, all the wind vectors at all the altitudes and geographies in that entire area. Well, so the weather map won't tell you. That'll just tell you the overall weather. You can put up 1 weather station or 2 weather stations. That'll tell you what the weather's like there. You can fly the drone around and know what the weather's like around the drone itself. But how do you do the entire wind vector field for the entire area at a resolution that's sort of drone sized? that's really an unsolved problem. There's some efforts in doing that with Doppler radar. You can certainly do try to measure wind and gusts on the vehicle itself, and then to kind of project that into a vector field. But it's an interesting problem. We're going to be resolving that later. You saw that AirSim is highly focused on perception, and there it's not just cameras, but it's lidar, depth sensors, radar, sonar, and things like that. We have to simulate all those sensors, and then you have to, when let's say you're looking at a surface and you want to see, how can I see that? Well, which sensor? Can you see it with your cameras? I don't know. Is it nighttime? Can you see it with lidar? Possibly. Is it large enough to hit your resolution? What about radar? Well, what about the absorption of the surface to a radar? Does it bounce radar or does it not? And so we have to now model the material properties of the environment to get that right. And then we get into the stuff that was covered in the IRIS talk about detect and avoid and traffic management. There's quite a lot of good work, especially done by NASA and the FAA in the past. But detect and avoid in particular is a little difficult. Now, we don't have a lot of real world data of collisions, thank God, because those would be bad. And we don't want to go up and fly airplanes at each other all the time, because that would also be dangerous. And so now we need to kind of procedurally generate realistic collision scenarios, approach scenarios, combinations of vehicles, and that not only you are likely to see, but also the ones you're unlikely to see, but not impossible. And so that's going to be we're probably going to use things like generative adversarial networks. And there's been a lot of work on self-driving cars to model pedestrian car road combinations, including really unusual ones. And so we're probably going to build on some of that work in that domain. Then we get to the question of how do we prove the fidelity, and I'm actually doing a lot of work on this right now. There's something called a Thiel coefficient, which is it actually comes out of Shannon information theory. It's information entropy, but it's basically you take two data sets and just sort of figures out how correlated they are. And so we've created a little bit of a tool here that you can see on the left, where you upload two data logs, one real, one sim. You can then, let's say that their coordinate systems are reversed. You can, quickly align their coordinate systems. You can sort of move them around so you align their timestamps, and then you can drag over the area you want to see the correlation, and it'll generate a Thiel coefficient. And we're doing this with some of the same teams that are working with Microsoft and the AirSim. This is Autonomy and the University of North Dakota. And as you probably saw in the earlier demonstration, they're using a wind turbine field to do their research. That's actually really useful, because wind is the number one thing that we need to simulate. And so not only do the wind turbines have, they have turbines, so they have, they know what the wind is at the turbine level, but also it's a wind farm, and so there's a really well characterized, wind environments and structures and turbulence around the structures, et cetera. So watch that space, but we're going to be, delivering some initial takes on the fidelity of AirSim against the real world, and also PX4, because that's what it's based on. And we're going to find out it's not going to be perfect. No, it's not going to be perfect. The question is, where does it matter? How predictive is it, and how do we make it better? So I just want to finish with this last slide before I take some questions. This is an ongoing research project that we're doing with an industry working group. You can see the list of the people we're working with right now. Obviously, I fully intend to add the GE folks and the IRIS folks, to say nothing of the Alterian folks to this going forward. We're really just getting started on this. It's an ad hoc group. It's not official yet, but we do, as part of the Drone Advisory Committee, I have been asked to interject it as a possible policy topic for the FAA and DNR in the future. And so what we really want to do is we want to kind of all get together, figure out what makes sense, prove it, with a couple pilot projects, and then deliver it to the FAA in the form of white papers, so they can then formally find a way to accept simulation data in lieu of real world data, and to help us do the DNR type certification more quickly, more cheaply, more reliably, so that more people can do it. So that is the end of my formal presentation. I think that is also the end of my window. So Ramon, what do you think? Should I take questions here, or do you want me to just take them on Slack?
You can take a few questions here.
Okay, good. Let me go to Slack here, and the questions popping up. I will. I think they're also probably on the YouTube channel, right?
Yeah, they're in YouTube channel too.
Okay.
Don't worry. Let's do this. Why don't we send the questions on the public PX4 Dev Summit channel, and you can join us there in the community?
Yeah. There are two. There's one question I can take right now, if you don't mind, off the
Go ahead, please.
Okay. This question was, how do the updated FAA requirements affect waivers flights of experimental drones during the initial R&D effort? And the answer to that is that many of these are intended to expire in October and be replaced by type certification. I think, and this will not surprise you, we're running a little late on this. It's a bunch of things, but it's a new process for the FAA. It's quite radical, and I suspect there probably will be some extensions. That it's not like everyone's going to be grounded in October. But what you are going to hear, if you already have an FAA waiver or exemption, you are going to hear from the FAA that they're going to want you to pretty much start entering the type certification process now. They're not going to want to continue extending the waivers if they don't have to. So get on a type certified platform. There will be several. Some of them are coming out of the PX4 community. There's at least 4 that I know of that are going through the process right now, including the 3DR H520G, which is our collaboration with Unique. So there will be choices, but in addition, there will be the work we're doing right now is going to make it a lot easier for anybody on PX4 to get into this process if you can partner with or are a U.S. company. So I will take the rest of the questions on Slack. Thanks so much.
Awesome. Thank you, Chris. Community, welcome. Thank you, Chris. That was super insightful and clear. I want to thank you in the name of the whole community for all the years of incredible service to our open source community. Thank you so much for the leadership, and talk to you soon. See you in Slack. All right, so let's see what we got. Hey, Ramon here, your host, Drone Code Program Manager. How are you doing? Are you still up? I don't see a lot of pictures on Slack yet. Thanks everyone for watching. Especially our friends in China. Did you know we have a mirror in China? Our beautiful partner Dimian Sang has hosted a mirror, and we have a lot of community members from China right now. It's like 5 a.m. in there. Thank you guys, thank you. We are going to be hosting an after party. I think we've been leaking this on purpose. But we're only sharing that through Slack, so make sure you join us on Slack. Our community volunteers are going to be posting a few links in there so you can get an invite. The after party is not going to be streamed through YouTube or any of our social media channels. It's going to be an invite-only party, so make sure you get your invite before the next session ends, because there's going to be a short window where you can get invited. So make sure you stick with us till the end.